All right, welcome to JM Lectures. This is the 5th unit of the grade 11 physics, work, energy, and power. If you can see that right here, that says power, okay? So we are doing the 8th question in the series, and this question says, an object of mass 1 kg moving with a speed of 2 meters per second was acted on by a force that produces an acceleration of 2 meters per second squared. What is the change in kinetic energy of the object if the force is exerted on the object for 2 seconds in its direction of motion? So, wow, that is a whole lot of information. It's kind of overwhelming, but it always helps to write down what you have. I cannot repeat this enough times. Write down what you're given and write down what you're required, right? So let's do just that and write down exactly what we are given, right? So we can first see that we have an object of mass 1 kg. So we can write the mass to be 1 kg. And then we know the speed to be 2 meters per second. I'm just following the questions it says there. I'm just following the question itself. The speed is 2 meters per second, right? And then it says that it was acted on by a force, but it does not give us the value of the force. But it was acted on by some force to produce an acceleration of 2 meters per second squared. So we see the acceleration is 2 meters per second squared. Our question is, what is the change in kinetic energy of the object, right? So let's write the required right here. The required is the change in kinetic energy. So it says, what is the change in kinetic energy of the object if the force is exerted for a time of 2 seconds, okay, in the direction of motion? It's important to know that because you can only use the force is equal to mass times acceleration, or the second law of Newton. You can only use that if the force is applied in the same direction as the motion, or in this case, the same direction as the acceleration, okay? So when you look at it like this, it's not that much information, right? But anyway, how you would tackle the situation is to first write the formula. So let's do just that. And for the solution, let's write the formula of change in kinetic energy, okay? So change in kinetic energy, whenever you see something that says change, usually all you have to do is subtract the final value from the initial value, okay? So if you know the formula for kinetic energy, that would be half mv final squared minus half mv initial squared, right? But you can see that we have a lot of things in common here. We have half in common here, we have m in common here. It's only the v final and the v initial that's a little bit different. So let's take the common out of half m is equal to, half m times v final squared minus v initial squared, right? So that's the formula that we're going to use to find the change in kinetic energy, right? So let's look at this formula. Let's look at this formula we have here and see what we have and what we don't have, right? We have the mass of 1 kg. We don't have V final, but we do have V initial. So this value right here is actually the initial speed, right? So we're going to have to find a way to find this final velocity, right? Luckily enough, we have a bunch of stuff that we haven't used yet, the acceleration and the time, right? So let's try to find V final using the quantities that we do have. Well, the formula for acceleration is in fact V final minus V initial over time. So we can straight away see that we have everything we need to find V final. So let's just plug in numbers after that. The acceleration would be 2 meters per second squared, right? Would be equal to the final velocity, which we're looking for and we don't know, subtracted by the initial velocity, which we do know to be 2 meters per second, divided by the time, which is the value we haven't used yet, a value of 2 seconds. So let's do some crisscross applesauce to get 4 meters per second is equal to V final minus 2 meters per second, right? Take the 2 meters to that side and we'll get 4 plus 2 or 6 meters per second is equal to our final velocity, right? So we needed that value. We needed that one value of V final to fill in our formula, right? So now that we have that, we can find the change in kinetic energy. So we're going to just plug in that value here and find that the change in kinetic energy is equal to half the mass, which is 1 kg in this case, 1 kg times the final velocity, which we just found here to be 6 meters per second squared, minus the initial velocity, which we already knew to be 2 meters per second squared. Oh, I don't know if you can see that. But anyway, the change in kinetic energy is going to be equal to just some quick math after this. 1 times 1 is still 1 over 2, multiplied by 6 meters per second squared would be 36 meters squared per second squared minus 2 meters per second squared would be 4 meters per second squared. 4 meters squared per second squared. All right, so we can just subtract those two. The change in kinetic energy is equal to half the value of 36 minus 4 would be 32 meters squared per second squared. But meters squared per second squared is actually joules, so we can actually change this value to change in kinetic energy is equal to 32 divided by 2, 16 joules. Okay, so it looks kind of long, but that's just some math. Yeah, you're just going to have to trudge through it. The kinetic energy is going to be equal to 16 joules. So one more time, all right, let's check if we have it in the choices first. Yep, choice D is 16 joules, right? So one more time, you just write down this overwhelming amount of information, right? And you write down what we required. So from your required, write down your formula and see what you have and what you don't have. You usually are missing one thing, or maybe you have everything and you just plug in the numbers. But since we're missing this one thing, we have to find a way to find this final velocity. There are a lot of ways to find it, but you have to find it in a way where you have the information to find it, right? We can see that we have acceleration, we have time, and we have the initial velocity, meaning we can use the acceleration formula to find V final, right? And don't forget, the point of finding this is to plug it right back into the formula here, and after that is just some math to get to our final answer, 16 joules. And that's it. All right, the next question we have here is question number 9, and this question says, a boy pushes a block over a 12-meter distance within 6 seconds. The force applied by the boy varies as shown in the diagram below. What is the average power loss by the boy? All right, so we have the diagram here, and this diagram shows the force applied on a block by a boy over a certain distance. So give me a second for me to redraw this graph here. All right, so this is the graph that we have here, and this graph is a force by displacement graph or by distance graph, depending on, no, all right, it's a distance graph. So it's a force times distance graph. So what this graph is showing us is that the force applied on this object is not the same, all right? So the boy first doesn't apply any force on the block, and in the first 3 meters of it traveling, it increases to a force of 4 Newton, right? And then from the 3rd meter to the 9th meter, it stays at that force of 4 Newton, and from the 9th to the 12th, it decreases right back down to 0 Newton, right? So this is a kind of graph that shows a variable force, all right? It's different from most graphs because usually you have a force that's consistently being applied onto an object, but in this case, it's a variable force. But fear not, because we can still answer the question either way. So the question is asking us about power, and power is simply the rate of doing work, right? It's just work over time. But what is work? Well, work is the result of a force being applied on a body, over a certain distance. You see how this might be applied to the question, right? Or let me write that down. Work is equal to force over distance. Work is equal to force times distance, or F times X, we can say, right? It's the product of two vector quantities, but we still get a scalar quantity. But anyway, so work is equal to force times distance, right? So if you've seen the previous questions about kinematics, when we were looking at a velocity versus time graph, we said that even though we only have force and displacement here, or force and distance here, you can find out a lot more in this question, right? You can find out a lot more in this graph. One such thing that you can find out is that the area underneath this graph, right? The area that we have right here, this area underneath the graph is in fact the work done, right? Finding the work done is as simple as just finding the shape of this area, because work is equal to a product of two things, and simply area is equal to the product of these two things here, right? So work is equal to force times displacement, or force times distance that we said here, and that will give us the area. So finding the work would be simple as finding the area. Finding the power is simply dividing that area, or that work we found, by the time, and we have the time given here. In fact, let me write that down. Some of the things that were given here, we're given this graph, first of all, but on top of that, we're given that it traveled a total distance of 12 meters, which is also part of the graph. But additional information that we have given is that it traveled for, the boy was pushing the block for a time of 6 seconds. We're going to leave this later to find the power. But first, let's find the work, right? So if work is equal to area, if work is equal to this area that we found, that we have to find on this graph, is just as simple as finding the area. So in this case, we can divide this area into a triangle and this like rectangle we have here, another triangle, but this is actually a trapezoid, right? So there is a formula to find the area of a trapezoid. If you don't remember that formula, don't worry, just find the two separate areas and then the area of the rectangle. But it's much easier to just use the formula of a trapezoid because this is an isosceles trapezoid. You can see, I didn't really draw it properly, but it's a perfectly isosceles trapezoid. It's perfectly symmetrical. So finding the area, right, which is basically finding the work, right? Finding the work in this case would be finding the area of a trapezoid. And the area of a trapezoid is half base 1 plus base 2 multiplied by the height. So in a trapezoid, I'm going to go into a little bit math here. This bottom, or it doesn't matter which one you call it, but this side of the trapezoid, you can call it base 1, and this side of the trapezoid, you can call it base 2, and the height is just literally the height of the trapezoid. So after this, it's just plugging in numbers. The work done would be equal to the area, in this case. Let me say the area is equal to the work done, right? And that would be half base 1 is the distance from here to here, right? So that would be from 0 to 12, right? So that would be 12. Plus base 2 would be this distance right here, right? The distance from this point, 3, 4 to 9, 4. The x distance from this point would be from 3 to 9. Again, don't take 9, don't take 3. It's in fact 9 minus 3. So 9 minus 3 would give us a value of 6, and that would be our base 2. That would be this length right here. Multiplied by the height is simply this height here, and we can go and see that it's a value of 4, right? Therefore, the work done would simply be adding and multiplying these values. 12 plus 6 is 18. Half of 18 times 4, and we can simplify that to get that the work done will be 36 joules. That's the unit of work. If I were to put the values properly, I would have gotten joules. But anyway, that's the unit of work we have here. So we have 36 joule as the work done. But that is not our question. The question isn't about work, but it's in fact about power. We just needed to find work in order to find the power. So let's plug in the numbers again. Power is equal to work over time. We just found the work to be 36 joules, and we can plug in the time that's in the given to be 6 seconds. That will give us a final answer of 36 divided by 6 watts, which is the which is the unit of power. So that 6 watts will be our final answer. And if we look at our choices, we see that it's answer C. So 6 watts is the total power used by the boy when he was pushing this block, okay? So you can see here that even though the graph given is a force times displacement graph, we were able to find work, and then we were able to find power, okay? And that's it.